This ETABS tutorial will show how to generate a synthetic earthquake matched to a specific response spectrum. This allows the user to create a time history with a similar frequency content and building response as a given response spectrum, allowing one to replace a pseudo-dynamic analysis with a full time history analysis. This may be done in ETABS using the define functions time history command. We start by selecting a function type of match to response spectrum and then click the Add New Function button. On the time history matched to response spectrum form, we will name the generated time history synthetic frequency. There are two ways that the time history may be matched, using either the frequency domain or the time domain. We will start with the frequency domain, but we'll add another case later for the time domain. The next step is to select the target response spectrum. This is the response spectrum we are attempting to match with the generated time history. The program default is an ASCE 7-10 spectra, but we could also select another previously defined spectrum. For this example, we will use the program default, which is in G units. The target spectrum is shown here, and for future reference, note that this curve has a spectral acceleration of approximately 0.82 g at a period of 1 second. Please also note that this target response spectrum has a damping ratio of 5%, and the synthetic time history will be matched at this damping ratio. Next, we must select the reference time history. This time history serves as the starting point for the synthetic time history. When working in the frequency domain, it is deconstructed using Fourier analysis, and the resulting functions are then scaled such that the response will match the target spectra when an inverse Fourier transform is performed. The reference time history is shown here. The program default is the El Centro earthquake, again in G units. Again, we can use any previously defined earthquake, such as the Newhall time history in inch units, but for this example, we will use the default. The next step is to set the matching parameters. Typically, it is best to attempt to match the time history to a subset of frequencies and not across the entire range, and this is what we will do here. We are now ready to create a matched time history record. On the form, we can see how the response spectra for the reference time history lies below our target. However, when we plot the matched time history, we see that there is relatively good agreement, especially for the overall shape. If we zoom in, we can see that there are regions where the generated response is slightly higher than the target, and we will need to keep this in mind when we review analysis results. Next, we will look at the frequency content. Here we can see how the content differs between the two time histories. There are a number of different ways this data can be viewed. Lastly, note that our synthetic match time history is now shown. With the frequency domain matched record defined, we will quickly generate another record using the time domain to see what kind of match we get. We will name this record synthetic time. Again, we will use the program defaults for both the target response and the reference time history. And we'll also use the same user-defined frequency range. We will leave the time domain parameters with the default settings. We can now match the time history in the time domain. Here we see very good agreement between the matched and target spectrums. Again, note that a matched time history has been generated. Now we will perform an analysis using the time histories just generated. Our model is a simple cantilevered column that has a fundamental period of 1 second. We will set up 2 load cases, one for each of the time histories. We start with the frequency domain earthquake. And we'll use linear modal. We will apply the earthquake as an acceleration in the U1 direction using the synthetic frequency record with a scale factor of 386.4. We will use 600 time steps with a step size of 0.02. We will set the modal damping to 0.05 to match the target spectrum. Next, we will create another load case for the time domain history. This time we will use linear direct integration, although we could use modal here as well. This time the acceleration function will be synthetic time. With the same number of time steps, and again we will set the damping to match the target spectra, which use 5%. We can now run the analysis. Let's start by verifying that the period of our single degree of freedom system is approximately 1 second. And it is very close. Now let's view the plots of the acceleration at the top of the column. We go to the Display, Plot Functions command, and we'll create a new plot function for joint acceleration. We will name it Accel, and it will be at story 1. We want a response type of absolute acceleration. Plotting this trace For the time history load case using the frequency matched record, we see that the peak acceleration is approximately 392 inches per second squared. And although this is greater than the value expected from the target spectra of 0.82 times g, or 317, it is reasonable based on the initial matched response spectra we generated. If we switch the same plot to the load case using the time domain record, the maximum acceleration is now reported as 317 inches per second squared, virtually identical to that anticipated from the target, a very good match. Thus, it may be advisable to generate synthetic earthquakes using both time and frequency domains to see which matches the target spectra closest, especially in critical frequency ranges. This concludes this tutorial on generating synthetic earthquakes.